You probably have heard of the following theorem due to Euclid more than 2000 years ago. Euclid's theorem says there are infinite many prime numbers. And you might also know the following simple proof, still due to Euclid, by contradiction. This might be one of the first proofs by contradiction in the history of mathematics. So suppose there are only finitely many primes, denoted P1 through Pk. Suppose these are all the primes. Then consider the number n equal to the product of all of these, plus 1. Because each prime number is always greater than 1. 1 is not a prime number. The smallest prime number is 2. So this guy must be greater or equal to 2. It follows that n must have a prime factor. Namely, there must exist a prime number that divides n. However, for any I greater or equal to 1 less than or equal to k, P sub I does not divide n. And this will be a contradiction to the fact that n must have a prime factor. And that is the end of the Euclid's proof of the theorem that there are infinite many prime numbers. The proof given here might not be very interesting to you because you might have seen this many times. But what we do when we think math is not interesting? When we think math is not interesting, we ask questions. You observe that the proof above actually shows that the infinite set consisting of all positive integers, 1, 2, 3, etc., contains infinite many primes. So, what is the natural question that you want to ask just looking at this sentence? I'll let you think about it, what question you are going to ask. And then I will give you a possible question to ask. So one possible question that you might want to ask based on this is that what kind of infinite subset S of the set of all positive integers contains infinite many primes? This is a very good question. However, if you just ask a question like this, it is not very easy for the mathematical study. A more professional question goes like this. What kind of infinite subset S of the set of positive integers contains infinite many different prime divisors? And by this we mean if you consider set P sub S defined as the collection of prime numbers such that there exists a positive integer in S such that P divides N. And let me make it clear that this notation means the set of all primes, namely 2, 3, 5, 7, 11, etc. That S contains infinite many different prime divisors means that this set P sub S is infinite. So this question will look more professional because you are really using the divisibility that is given in the definition of prime numbers. This is a very hard question, and many progresses are made to give an answer to this. Let me start with one big progress. This is in the year 1912, and the result is due to the mathematician Schur. So Schur proved that for every non-constant polynomial P of x with integer coefficients, the set S which is defined to be all those values of this polynomial that are non-zero is a set such that P sub S is infinite. In particular, Schur's theorem implies the Euclid's theorem, because if we take P of x to be equal to x, then the set of positive integers, so Schur's theorem implies the Euclid's theorem. Since in this case, the set of all possible prime divisors of this set will be precisely the set of all prime numbers. Okay, now 100 years later, in the year 2012, the mathematician Elsholtz generalizes the theorem of Schur as follows. However, in order to introduce Elsholtz theorem, we need two definitions. Let S, now instead of considering a set, let us consider a sequence, starting with S1, S2, S3, and so on. Be a sequence of integers. We say that first, S is almost injective if there exists a constant C such that every value of S occurs at most C times. In other words, this means no value of S can repeat arbitrarily many times. The number of repetitions of any value of S must be bounded by this constant C. You should also notice that this C, without loss of generality, can be assumed to be a positive integer, because S is a sequence of integers anyway. And that is our first definition. And the second notion is as follows. We say that S is of sub-exponential growth if the absolute value of the term S sub n is bounded above by 2 raised to the power of 2 raised to the power f of n for all n. Where f from the set of positive numbers to r plus the set of positive real numbers is a function with a growth rate slower than log base 2 of n. So in the mathematical language, this means this guy converges to 0 as n goes to infinity. So this means Sn cannot grow too fast. This is a second notion. Now, with those two notions, we are ready to state our theorem due to Elsholtz. The theorem states as follows. If the sequence S, starting with S1, S2, S3, etc., is almost injective and of sub-exponential growth, then the set P sub S of primes that divide some member of S is infinite. That's a statement of the theorem due to Elsholtz. Although it might be hard for you to imagine why those conditions could possibly guarantee that P sub S is infinite. Maybe let me try to provide you with some motivation just from the definition of those two notions and by some examples. So this will be the motivation by example. First, why would need the almost injectivity? Why we need that every value of S appears at most C times for some constant C. If you just consider the following simple example, a sequence where each member is 2, constantly 2, then this is not almost injective. That divides some elements in S. So P sub S is not infinite. Or S is equal to 2, 4, 4, 8, 8, 8, 16, 16, 16, 16. And you have seen the pattern. The 2 appears only once, and 4 appears twice, 8 appears thrice, and 16 appears 4 times, and so on. So the number of times that 2 raised to the power n occurs is n. This will be another example that S is not almost injective. For both cases, we have P sub S is just 2, because the only prime number that could possibly divide some element in S will be just 2, no other prime numbers. And this set is finite. This gives you some kind of feeling why the almost injectivity is necessary. So why do we need the sub-exponential growth condition? If the sequence is not growing sub-exponentially, so this is not satisfied. In extreme case, say f of n is just equal to log base 2n. If f of n is just equal to log base 2n, then 2 raised to the power f of n will be just 2 raised to the power n. So in this case, S will be a sequence 2, 4, 8, 16, 33, and so on. In this situation, P sub s is just also the singleton 2. Because in a situation like this, S grows too fast, and as a result, it might not catch infinite many prime factors. And this gives you some sort of feeling that the growth rate should not be equal or bigger than log 2 raised to the power n. However, we need a rigorous proof to justify this theorem. The proof is very beautiful, and at the same time, it is very elementary. It is just about a smart counting of elements in the set in different ways. So now let's go to the proof.